You ready? Okay. Oops. Yeah, you're right. Whoever said Monday, you should have been more persistent in pointing out that it's Monday 9 a.m. So the assignment's due Monday 9 a.m. I feel sorry for the people who are just watching the video and watch the first 5 minutes of the first video and all think that it's due midnight Sunday. Better tell them all. Well, who cares? I mean, if they finish early, that's good. So now you can all do the quiz on Sunday night and then spend the rest of the night working on assignment 1. Or you could do the quiz now, it might not be a bad idea. Alright, let's get back on to this set ADT. So, we had a very simple abstract data type, simple set of operations, wanted to look at a number of different ways of implementing it. So remember that our standard representation for abstract data types that we'll be using in this course is we'll have some kind of structure that represent a representation of the ADT object, which users don't see. All they see is this pointer. So clients for the ADT just see that, they can't look at the internals. The operation, so you can create a new set object, initially empty. You can free up the space allocated to a set object, display it, or fill up a set from numbers stored in a file. Why is that being loud? I don't know. And then standard set operations like insert, delete, union, intersection, cardinality. And we looked at an implementation that just involved an array. We had 2 versions of the array. One was fixed size, where you decide up front the maximum cardinality of my set is going to be 1,000 or 2,000 or whatever, max elements, and that's it. Once you've got 2,000 elements in the set, if you try to do set insert, it ought to fail. I'll tell you something like the set is full. If you want more flexibility, then we can define it as a dynamically allocated array, and we can use the realloc function to change the size of that array. If it fills up, we can make it bigger. All right, another obvious dynamic representation for a set would be to do it as a linked list. A very simple set representation might simply be a pointer to the first element in the list. Possibly more useful set representation might be to hold the number of elements plus a pointer to the first and a pointer to the last. Either of those would be fine. They'll differ in the cost of various operations. So if you think about it, it's pretty obvious that this representation here, if I want to work out the cardinality of the set, how many elements are contained in the set, the only way I can do that is to scan along the list and count the number of nodes. So that's an order n operation, which is potentially expensive if the set is large. On the other hand, if I've got this representation here, then I want to work out the cardinality, I can just read it straight out of there, regardless of how big the set is. So that would be order 1. So if cardinality was a very common operation, you might want to consider this implementation. Of course, the downside of this implementation is more storage space, not much, more storage space, so that's not really bad. The other cost is that there's going to be a little bit more work every time I insert a new element. So I have to, as well as just adding it to the list, I have to update this counter to tell me where it is. A third representation, of course, if I don't care about the order of elements in the list, which I apparently don't looking at here, is I can simply have a single pointer to the first element in the list, and every time I insert a new element, I just stick it at the front, which is a very easy way to insert things into a linked list. All right, so if I'm going to use a linked list representation, what's the cost analysis going to look like? To do an insertion, I have to scan the list to make sure that the value I'm trying to insert isn't already in the list. Okay, to do that, that's an order n operation, scanning the list from start to finish. If I don't find it, sure, I can insert it at the head, and that's relatively cheap, but the cost comes in this operation here. Deleting an element from the list, similar problem. I've got to find the element in the list, and then I've got to unlink it. Finding it involves a scan. Unlinking involves a little bit of pointer rearrangement, which, while it might be messy to write, isn't expensive, but overall the cost is still order n because of the need to find the node to delete. Similarly, same with member, I have to scan the list to find where the element's contained. Even if the list was actually in order, I'd still have to scan it up to the point where I found an element larger than the one I was looking for. So either way, it's going to be order n. Cardinality, if I've got an n elements thing in the struct, then it's order 1. Union, all right, this is slightly more interesting. Stop standing on it. Union involves getting the elements of both sets and putting them together. Easy way to start is simply make a copy of one of the sets and then run through the other set and insert it into the new union set. Remember that the union operation produces a new set, it returns a set result. Intersection, I'd have to scan through the first element of the first set. For each element in that set, I'd have to check whether it existed in the second set, and if it did, I'd add it to the new set. So for each element, I've got to do a scan of each element in the first set. I've got to do a complete, or potentially a complete scan of the second set. So that would be order n. In this case here, certainly the first, so if the size of S1 is n, there's certainly an n component in that. No, I don't think that order is right there. So, having created a copy of S1, I then want to run through each of the elements in S2, check whether they're already in the list, and if they are, I'd insert them into the list. Oh no, maybe that is, no, it's m times a search of the list. So in fact, this really should be order n plus m n, if you like. Okay. So the n term comes from making the copy of the first list, scanning along, inserting it into the new set. When you're making a copy, you don't have to do duplicate checking because you know you're starting from a set and you can just straight away copy everything across. But when I'm trying to do a union, I want to make sure that I don't insert a value that's already there. So for every element in S2, I have to scan the existing new set and check whether that value is not already there coming from S1 and not added. So in fact, for every element, m times, I'm going to have to do a scan of the set, of the new set. How long is the new set? Well, it starts out at length n and it ends up at length n plus something, depending on how many duplicates there are between the two sets. I would argue that you could probably characterize this as an n plus mn term, and in fact the cost would end up being the same as the cost for this, the order cost, even though there's an initial upfront cost here of order n, but remember that we forget about lower order terms. If we don't have n elements, as I mentioned before, the cardinality becomes order n. And even if the list is ordered, it doesn't change the complexity. There's still a scan, but potentially you scan less of the list, but the amount you scan could be on average n over 2 rather than n, but for complexity analysis, they're both still linear, linear complexity. They grow proportional to the size of the list. One just grows a little bit slower. Right, so that's linked list representation. Another kind of representation would be to use a hash table. So basically what a hash table is, it's a way of indexing based on key values, where key values can be arbitrary kinds of values. They can be numbers, they can be strings, they can be whatever. And the set of values that you can use for keys can be much bigger than the actual table. If you think about a normal array, if I wanted to store values in a normal array, and I had a range of values from 0 up to n-1, then I could simply use the value as an index and put it in and access the array like that. So what we're doing with a hash table is we're taking the key value and running a function, running it through a function that gives us an index into the hash table. And that basically tells us whereabouts this object belongs in the hash table. Now, if you've got a large number of objects and a relatively small hash table, you're going to have the fact that several objects with different key values will end up coming up with the same hash value, and therefore want to go in the same spot in the hash table. Now, if the hash table is a fixed size, there are techniques for dealing with that, and we'll in fact, forget about fixed size. If everything is stored inside the table, we can't obviously put two objects in the same location, so there are ways of manipulating or deciding where to put the second object that has the same value. But in our case, what we can do is we can simply use a technique called chaining, where basically we hang a linked list of each of these entries in the hash table, and we have something like this. So if I want to insert the value 4 into the hash table, the first thing I'm going to do is compute the hash function. So 4 mod 4 gives me 0, and that means that 4 belongs in this chain here. So I'd add 4 at that point. If I subsequently want to insert 12, say, so the value of x is 12, the key is 12, I'll take 12 mod 4, that's 0, so I'll say, all right, 12 belongs in this chain here. It's part of this bucket, if you like, of objects, and so I'll add it to that list. Okay, so always the first step is take your key value and compute an index into the hash table, and then insert the object into whatever's attached to that element in the hash table. So in this case, everything's a list. Now you might say, why is that different to the linked list representation? Well, one way it's different is that, yes, it's a bunch of lists, but potentially the lists are, in this case, a quarter the size of the original one. So if we go back to that linked list representation, and we had 12 items in the list, there'd be a linked list of length 12. So every time you needed to do a duplicate check, you'd have to scan potentially all those 12 items. In the case of a hash table like this, you can see that the lists are relatively short. You know, if we had a few more, if we had up to 12, potentially each list is going to be length 3. So doing a duplicate check in this case involves first doing a simple computation to work out which particular list we're interested in, and then doing a duplicate check by running along that list. So the average list length is going to be much shorter here. However, it's still order n, because the length of the list is proportional to the number of items that we've inserted into the array. This will be true if the hash table is relatively small. If the hash table was quite large, let's say it had 1,000 elements in it, we'd have the potential for 1,000 lists. It's pretty likely, if we choose an appropriate hash function, this is not a useful hash function, not a useful hash function, but if we had 1,000 items and 1,000 elements in the hash table, and we had a decent hash function, then it's quite possible that all of our lists would be of length 1, which has quite a nice property. The duplicate checking, we compute a hash value, which is simple numeric computation, gives us an index into our table now of size 1,000. We go there, there's a linked list, well, there's a linked list, but the linked list is always, pretty much always going to be length 1. So we only have to check one item each time. So that's a probabilistic thing. Most of the time the list will be length 1. Occasionally you might get two key values that hash to the same place, and you'll have a list that's slightly longer, maybe length 2. But most of the time, with an appropriate hash table size and an appropriate hash function, the list would be length 1. So that's going to be quite an efficient way to do things. So in fact, insertion would be order 1, deletion would be order 1, set membership, order 1. In all of those cases, you compute the hash function, you go to an entry in the hash table, that's a link to a list of length 1, you look at the item in that list, and if you're doing membership, if it's the value that you're looking for, you found it. If it's not the value you're looking for, you didn't find it. But hash computation, look at a list of length 1. So that's pretty much, if you've got a well set up hash table, that's about as good as you can do for scenarios like this. Let me see. Now I've got, I think, I don't know, maybe I don't. Do I have it? Oh, I don't have an implementation. Oh no. Oh, do I have time to write one? All I've got is a framework. Yeah, let's take a look at how we might do this. Okay, so our set representation, we may as well count the number of elements. And each element in our list is going to be a link to a linked list, and so we need to define our linked list data structures. Of course, if we already had a list ADT, then we could just use that. I'm assuming that we don't in this context here. So we'll do our standard definition. Which will be value and link. Alright. And so what we have here is an array of lists, an array of links. So we can still call them elements. How big do we want to make this array? Well, in this case, we make it a reasonable size so that we're not going to have so many collisions, so that the chains won't be quite so long, so the linked list won't be so long. So we could make it, I don't know, let's pick a random number, 1001. It's a good idea in these contexts to pick a prime number. I don't know if 1001 is prime. Someone can check and let us know. So anyway, a relatively large table. All right, checking whether a set looks plausible. Well, one thing we could do is check in fact, that's about all we can really do. I think there was a question about that in last week's tutor. A linked data structure like this, oh no, sorry, you can do better than that. All right, if S is null, then the set is not valid. We should never have a null set pointer. Every set variable ought to be initialized using new set. So if the set pointer is null, that's an invalid set as far as we're concerned. If it's not null, then one thing we could do is check whether the nlms component has a sensible value. What would a sensible value look like? Yeah, I didn't quite hear that, but it has to be non-negative, right? So if it's less than 0, we got a problem. There can't be -5 elements in a set. So in that case, we might also return 0. If it was positive, then I guess one kind of sanity check that we could do is to run through the elements array and make sure there's at least one non-null value. Now this is getting, if n elements is greater than 0, I don't use C99, so I'm not going to put it in the for loop. Oh no, I've got a magic number. Oh my god. Whoops. Does anyone check whether whether 1001 is a prime number?
Is it in prime?
It what?
Is it in prime?
It's not. You got one nearby that is?
1009 is prime.
Okay, thanks. That'll do. Do you just know that off the top of your head, or?
Well, it's the lowest prime above 1000.
Okay. You do know that off the top of your head. Ooh, impressive. So, if we know that there's an element in the set, at least one of these lists has to be non-empty. So we can look for a non-empty one. We'll have to have a counter and we'll count it as we go. If the set elements I is not null, so we scanned through the hash table looking for a non-empty list because we know there's at least one element, and so here we can do a check. If nList is equal to 0, then there's something wrong with our set structure. We can't do much more than that. If we wanted to do even more work, checking how sensible it was, we could check that the number of nodes in all of the lists was equal to the value of n elements. That'd be a plausible kind of thing to do, but I'm getting lazy and can't be bothered doing that. So this will at least check that if we claim to have some elements, we've got a list to hold those elements. Alright, so there's a bunch of things that can go wrong. If none of those things happen, then we've got to return a result that says, yeah, it looks kind of valid, so we can just return 1 at this point. So we run through a whole lot of tests. If any of those tests succeed, it's an indication that there's something wrong with the set. If we eventually reach the end of the function, then, alright, nothing wrong with the set, so we're done. Alright. So, did I define that properly? Yes, good enough. Right, how to set up a new set? Remember, creating a new empty set. We need to allocate a set data structure. Oops. lazy and I'll use assert. Since we're in development mode, that's all right. And then we need to set all of the elements in the set to look like valid empty lists. And so we can do that pretty easily. Notice how I don't want to waste any vertical space, and then you'll say, why didn't you put the int definition inside the for loop? That would waste even less vertical space. True. Alright, so since I don't care that much about vertical space, I'll do that. What else? If I want to make this look like a valid empty set, yep. So I have to indicate that there are no elements. And then of course I don't want to return null, I want to return new. So I reckon that would probably do it. Alright, so probably the interesting thing to look at here, I'll define the hash function up here. Actually, is valid. If I'm not using that anywhere else, I could define that as static. And similarly, the rest of the world doesn't need to know about the hash function, so I could equally well define right, so this is the world's worst hash function, but it'll do for this. So that's going to give us one of the elements in the hash table, the elements array. Or maybe I should have called it a hash tab. Oh, that would make sense because that was what I had in the diagram. Oh no, I'll have to run through all these and check. Where is that? Alright, that'll do. Okay, so I'll just do maybe one. Where's set insert? Set insert. Okay, so we can certainly do that check to make sure that S is a valid set. And if it was possible to check that N was a valid integer, we could, if we wanted to, we could say these are sets of positive integers and we could check whether N is greater than 0 or something. Alright, what to do? First thing we do is we compute the hash value of the key, which is the number that we're trying to insert into the set. The next thing we have to do, we go to the particular chain relevant to this hash value, and so let's go current equals s hash table position h is going to give us the start of the linked list. And then we can scan along that list. Looking for the value n. So this is our duplicate check. And if we find it, there's nothing more to do. So in fact, we could just take our lazy way out and return at that point. As soon as we discover that the value is already in the list, just give up the function. Otherwise, we need to I think I had node as a data type. Otherwise, I allocate a new node. Wow. do my standard check. Set the appropriate value. And then I've got to link it into the list. I would argue the easiest way to do that is to simply put it at the front. So new points to the element that's currently at the front of the list, which is this one. And then that points to the new. So that'll put the new node at the start of the list with the new value that wasn't currently in the set. So that's set insert for this. So you can see there is the potential for that to cost if the chains are hanging off the hash table are long. But if they're not, then we can do that relatively quickly. In particular, if all the chains are length 1, then that's going to be a pretty simple test, except that, what's wrong with it? Except I can't compile. Is it going to compile? I was thinking perhaps we could use GDB. Anyone spot the error? It's often easier to spot the error than have to go through GDB. GDB is useful if it's your code, because you can never see the bug in your own code. And it's really annoying if you've got a bug and you ask someone, this doesn't work, they will always spot it instantly and you feel like an idiot that you didn't see it. But it's just a fact of life. As you write the code, you build up a mental model of what your code is supposed to do. And if it doesn't quite do that, then it becomes very difficult for you to see. Anyway, what's the bug? If I start going around this loop, I go to the start of the list, I check whether the current value is n, and I return, that's fine. If the first element in the list isn't n, what happens? I go around the loop again, I look at the same current element. So I'm not advancing along the list, which you can spot pretty quickly if you use GDB, but don't have time. So obviously I left the standard linked list scan to the next item in the list out. Right, so hopefully that'll fix that. So in any case, the point was we can go quickly to the relevant list in the hash table. If the relevant list is short, beauty, we'll do that quickly. If the relevant list is longer, then we'll have to do some scanning to find it. Either way we have to scan, but if the list is always length 1, then we just do one test and we'll discover that current is null and we'll finish and we'll create new nodes to get at the front. So any questions on that? Have I got any other bugs in there that I didn't spot? No, you can go and play with the code then. Remember, this is all stuck online, you can grab it and do what you like with it. Alright, so the costs for an implementation like this, well, if the table has got k elements in, like 1009 that we just had, well, the cardinality, because we've stored the there was a bug. Why didn't someone yell at me and complain? What else have I forgotten to do? Yeah. Increase storage. No, we don't need to. I forgot to do that. So eventually I might notice that I always had 0 elements in my list, or at least this component of the structure was always telling me that I had 0 elements, even though I knew perfectly well that I had more than 0. So you've got to be a little bit careful about things like that. It's very easy to make those kind of errors by carelessness. All right, in any case, so the reason I just realised that was because I noticed that if we're doing the cardinality, we're reading the value of n elements, so we better make sure it's up to date. So that's constant cost. To work out whether a value x is a member of the list, of the set, what we have to do, we compute the hash function like we just did then, and then we scan the relevant list until we either find the value x somewhere in the list or we don't find it. So if we find it, we return 1. If we don't find it, we return 0. How much does that cost? Well, computing the hash function is trivial, doesn't cost anything, and certainly doesn't, it's order 1 relative to the size of the set. How much is this scan going to cost us? Well, it'll be, on average, the length of the chains will be n over k. So if we've got 2,000 elements in our set, and we've got that, if we had that hash table of length 1,009, then on average, each chain would have 2 elements in it. Okay? So n over k. So 2,000 over 1,009. So k is the table size. So remember that I said when we talk about complexity, we basically get rid of constant values from our formulae. So this is still going to stay as order n, even though we know that the cost is likely to be considerably smaller than having a single linked list. Okay. So, I mean, you could argue this is a case where the complexity is a little bit misleading. Insert, that was the example we just did. So we compute the hash value, do a duplicate check, scan along one of the chains in the hash table, and then add it, well, I added it at the start, which makes it even simpler. Delete, once again, compute the hash function, scan through the list, and if you find it, then unlink it from the list. All right, let's see if I manage to get this right. Union. So here, the simplest thing to do probably is to implement union in terms of the insert function. So start with an empty set, scan through all of the elements of the first set, and insert each of them into the new set, and then scan through all the elements of the second set and insert all of them into the new set. So the cost of doing that is, if you like, it's probably more like n times n plus m. So n plus m is the number of insertions that we have to do. Each insertion is going to cost something like that. So n over k multiplied by n plus m. And intersection is going to be a little bit similar. So we need to scan through the first set, and for each item in the first set, if we find it in the second set, we add it into the result set. So that's going to give us a cost something like that. One thing that we've done in a couple of places is that we've scanned through the items or the values in the set. That's easy to do if we know the structure of the set, but it's not easy to do for someone using the set as an ADT. They can't actually do that kind of scan. So in a lot of contexts, it's really useful if we're able to just traverse a data structure and one by one return an element from the data structure to a user. To do that, you can't do it in a single operation, certainly in C. What you can do is have an operation that says start the scan, another operation that says get the next item, and the get the next item can return an indication when it runs out of items. So the standard thing would be something like this. I haven't implemented any sort of scanning or iteration stuff as part of this, but what I'm talking about is we need another kind of object and a couple of operations. So an operation to start a scan and an operation to get the next item from a scan. Maybe I should call it scan. You know, I should have done that as a tute question. Maybe I'll do it for next week. How we might go about implementing this. So, we have an initial operation to set up the environment for doing a scan, and then we have an operation that says get me the next item, get me the next item, get me the next item, and it returns a pointer to the item. When it eventually reaches the end of the data structure, it can return null, and we can use that as an indication that we've reached the end of the items. And you probably want something to close down a scan once you've finished with it. Now that kind of thing should look familiar. It's basically what you're doing when you do fopen, fgets, 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 fclose. So opening a file to read, scanning through the file, and then closing it off once you reach the end. And fgets, you're doing line by line, so essentially an item is a line in that context. So this kind of thing is very useful for a lot of data structures, and if the user needs to scan through the collection, you need to provide something like this. There's no other way they can do it. Well, there is one other way they can do it. One really stupid way they could do it is they could generate all the possible values that might be in the set. For each value they could check whether it is in the set, and then they could use that, but there's a lot of possible values that might be in the set. So I'll just add that to one of the tute questions, so you can see how you think about how you might actually go about doing that. So that's one kind of operation that I hadn't talked about in this context. All right, let me do. Right, I'll just quickly get started on the final data structure. Oh, all right, there's an exercise. A perfect hash table, basically everything's going to be order 1. So you get absolutely the best performance you can possibly get. So a large hash table, a good hash function, all of those chains will be length 1, and the cost of every operation, go to a particular entry in the hash table, look at a list of length 1 and do something with it. So that'll be quite good. All right. Except for the last two, the union and intersection, you've got to do an order 1 operation multiple times, so it's going to end up as order n plus m or whatever. All right, another way to implement. Now, in this case, we have to make an assumption that we're going to restrict the set of possible values, or the possible values that might be in the set. So if we say, all right, we're only going to allow the values from 0 to 1,000 to be members of this set, then we could use a data structure which is basically just a set of bits. So to indicate whether an element is in the set or not, we're going to set a bit, well, to indicate that an element is in the set, to put it in the set, we'll set a bit corresponding to that value to 1. If we want to remove an element from the set, we set a bit corresponding to that element to 0. And if we want to check set membership, we look at the bit corresponding to that element and check whether it's 0 or 1. And if it's 1, then it's in the set. If it's 0, it's not. So we need one bit for each possible value that we might store in the set. So if there are 1,000 possible values, we need 1,000 bits. So essentially just an array of bit values. Now, you could use an array of integers and set it, you know, if the value 0 is in the set, then in set 0 is equal to 1. Obviously that's using 4 bytes to store a value which is either going to be 0 or 1, so that's not particularly good use of space. Alright, you might say let's make it an unsigned char or something like that. So we've only got 8 bits and we're using one of those bits. Even better would be to use just a single bit for each of the possible values to store in the array. But to do that, you need to know about bit operations in C, so I guess I'll talk about them next time. That's it for today.